All right, so today is not going to take the entire hour and a half, okay? Today's not going to take the entire hour and a half. I know we hit it really hard last week, so I want to try to give you a little bit of a breather today because I know that you had a lot of work over the weekend as well. So today we're going to cover one unit in PreCalc because in my personal opinion, I think this unit is a little bit more, I want to say meaty, right? It's got a little bit more going on to it in this first lesson than the next two. So today we're just going to cover the one more meatier unit here, okay? So hopefully everyone's okay with that. And my goal here is to spend about half of the class time dedicated towards this new content and then giving you the other half of the class time to either work on what's still missing from this weekend, right? Because a couple of us had a lot of things missing. So I'm giving you some time today to work on that, to catch up, or to just use this time for any of your work that you have in PreCalc, or for those that are in both, any of the work that you had today for Algebra 2. All right, so trying to make Mondays a little bit less painful here. All right, but if we can get started. All right, so for Unit 3, we're going to deal with working with trigonomic functions, okay? So a little bit more with trigonomic functions here, all right? I'll ask someone when we get there, but I'm wondering if this unit is something that, again, you already kind of covered in your geo-trig class, or if this is going to be something brand new to you, all right? So we'll get there in a second. Just an overview here of working with trigonomic functions, okay? You can read this on your own time, but basically we've been dealing with a lot of problems where, okay, I know the angle, what's the length, right? Now we're gonna kind of flip it and say, okay, I know the length, what angle do I need? Right, that's kind of what this is going to deal with here, is taking the opposite approach of what we've been dealing a lot with, all right? In order to do that, right, we're going to deal with this thing called the inverse trigonomic functions, okay, inverse trigonomic functions, all right, and to give you an example of this is designing a sprinkler here. So we'll watch this together because obviously, as you know, it comes back throughout the lesson. So let's watch.
Suppose you want to design a water sprinkler for your garden that is 12 feet in length. How would you design the sprinkler with water conservation in mind? Consider this diagram that shows how your garden and sprinkler will be set up. The sprinkler will be centered 2 feet from the garden. To conserve water, you need to find the particular angle theta that will minimize the amount of wasted water. How can you do this?
Okay, and for those of you that would be like me in high school, the real question I would ask is, do people really think about this? And the answer is actually yes, right? So there are a lot of things. One name for it might be a design engineer, right? Or just an engineer in general. Okay, so when people make products, right, they keep things like this in mind, like water conservation, right? You don't want a sprinkler that sprays water everywhere. No one's going to buy it, right? So believe it or not, people actually can take these things into consideration when they're making new products. All right, so if this is our idea here, okay, we can then obviously take this and turn this into some right triangles that we know how to deal with.
Looking at this triangle, you see that the angle you are looking for will be twice the angle marked in this triangle. How do you find this angle? You need to use inverse trigonometric functions.
Okay, so again, we've been dealing a lot with forward and reverse reactions, or basically inverse of each other, right? So again, in Unit 2 and in Unit 1, we dealt a lot with, okay, if I have sine of theta and I know that this is this length, it's this angle, right? But now we're going to deal with angles that maybe aren't as obvious here, okay? But we can still, if we have these two lengths here, okay, we can still use a trigonomic function here to figure out this angle, but obviously we need to take the inverse of it, right? We need to take the inverse of it, all right? And Yarlesk, help me out here. Did you guys ever deal with anything in geotrig called like arc tangent, arc sine, arc cosine?
I'm not sure.
Okay.
Yeah.
Yeah, that's fine. Quinn, how about you?
We messed with arc lengths a little bit, but no arc sine, no arc cosine and no arctangent.
Awesome. Okay. Okay. Well, perfect. And even if you guys did mention it a little bit, the fact that ERLS said maybe, not sure, means it wasn't a super big focus for you guys. Okay. They're trying to be funny. Arc, who goes there? All right. Basically, though, we can do this thing called arc sine, arc cosine, arc tangent, etc. Right, for the other three trigonometric functions. Okay, but basically, you have sine and arc sine. Okay, so those are inverse of each other. All right, same thing. Cosine, arc cosine, tangent, arc tangent. Okay, so those are inverse relationships of each other. So in order to understand what that means, we're going to have to first look at the domain and range of each of these functions here. Okay, so for example, if we're looking at sine of theta equals 1/2, okay, we're trying to technically solve what our theta is here, or what angle, when we plug it into this sine equation, would give us 1/2. Right, would give us 1/2. Okay, and this is one of those a little bit easier ones, right, that we talked a lot about. But when we're dealing with these trigonometric functions, we know that they go on and on and on for an infinite number. Right, they go on for a while, with obviously some exceptions and some zeros and points like that, right? But in general, they're going to keep repeating on. Okay, so technically we can have multiple points that will satisfy this equation here, right? And we'll take a look at what that means. But those multiple points are called coterminal angles. All right, they're called coterminal angles. So if we look at what the definition of that is they're angles of a circle drawn in a standard position if they have the same terminal side. I know it seems a little bit confusing. All right, so let's look at what this means here.
Recall that the x and y coordinates of any point on the unit circle are given by cosine and sine of the angle that determines that point. Since you are interested in when sine equals 1/2, you can mark this as follows. As you have seen, sine of pi over 6 is equal to 1/2. Does this mean that theta equals pi over 6?
Okay, well, does it? The answer is probably.
Here you can see that theta could also equal 5 pi over 6. Are these the only possible angles that will have sine equals 1/2?
Okay, and the answer to that is going to be no, because remember, it repeats and it's a circle. So this is going to go around and around and around continuously forever and ever. And it can go in the positive direction and it can go in the negative direction. All right.
It turns out that pi over 6 and 5 pi over 6 are just the beginning of the story. There are an infinite number of angles coterminal to these angles that will also satisfy this equation. Push the buttons to see some examples.
Okay, and again, coterminal means that even if this goes around, let's say it goes around one time, it's still going to end up at this exact length here, right? So it's one whole rotation plus pi over 6, or 2 whole rotations plus pi over 6. All right, same thing here. It could go around once and then an additional 5 pi over 6. So if I highlight over these, and unfortunately it doesn't let me to show you, so I can't move my mouse here at the moment. But if you look here, okay, if you look at the red, right, the red goes around. Okay, notice it goes around once. Okay, it goes around once and then an extra pi over 6, right? And if we remember that it's 2 pi, right, we have 2 pi plus pi over 6. That's how we get that 13 pi over 6. All right. Or if we go in the negative direction, the blue one's going in the negative direction, right? It went reverse almost the entire way around, okay, and it stopped at pi over 6, right? So it went in the negative direction. And then obviously green went around twice and ended up still at the same point of that pi over 6, right? But again, every time it goes around the circle, it has to add a 2 pi. Right, it has to add a 2 pi, because going around this circle once is an entire 2 pi. All right, and we'll, like I said, we'll digest this a little bit more here. But basically, these are coterminal angles, right? They can go in the forward direction or in the reverse direction. But regardless, the whole point is that they still end up at this line here. all right? And specifically for this line, it's where sine is equal to 1/2, right? Or our y coordinate is equal to 1/2. All right, same thing for 5 pi over 6. All right, it can go in the forward direction, the reverse direction, and regardless, all right, there's multiple angles that'll satisfy this, where sine of our angle will give us this 1/2. All right, and something I want to point out here is that pi over 6 and 5 pi over 6, these guys together are not coterminal angles. All right, they are not coterminal angles because they're obviously ending at different points here. All right, so these 2 points both satisfy our requirement for sine of theta being 1/2. All right, but when we're dealing with coterminal angles, right, the coterminal angle for pi over 6 would be that red one, that blue one, and that green one. So 13 pi over 6, negative 11 pi over 6, 25 pi over 6. Okay, those are the coterminal angles for pi over 6. All right, and obviously there's more depending on how many times you want to go around the circle here. All right, same thing. Coterminal angles for 5 pi over 6 is the 17 pi over 6, the negative 7 pi over 6, and the negative 19 pi over 6. All right, so again, they're angles that end up, no matter how many times they go around, forward or reverse, they're going to end up at this same ending point, right? The same ending point. All right, so then when we're talking about all of the answers that could possibly be correct for this, all right, we're going to introduce this thing called a solution set. All right, a solution set, and hopefully that's not unfamiliar to you guys. All right, a solution set is just all of the possible answers that make your equation true, all right, or that satisfy the equation. So if I'm looking here, right, at denoting our solution set, all right, we can represent our solution set by writing our theta in as an x value, right? We can write this in our standard f of x or our standard function notation. All right, we can just write this. We're solving for our angle here of theta, so we can just write this as sine of x equals 1/2. All right, and once we've got it in this form here, there are 2 commonly used notations that we can use to solve this. All right, and these are going to be those inverse functions. All right, so the first one here is this arc sine. All right, this arc sine. All right, or another way of saying arc sine is sine to the negative 1. All right, sine to the negative 1. All right, and this one is the one that you're going to probably deal mostly with. 1, it looks like an inverse function. All right, and 2, this is what you'll see on your calculator. All right, this is what you'll see on your calculator. Most of them will say sine to the negative 1. It will not say arc sine. All right, but basically what we're doing here is we're saying, all right, our inverse function of sine for 1/2, right? Or what are all of the x values that if we plug this in, will give us a value of 1/2. All right, so we're taking the inverse of this function. So what we do again is we write it as our inverse sine function, so sine of negative 1 or arc sine. All right, we put our value that we're trying to solve for equals blank, right? And what this is going to equal is all of the answers that will satisfy our theta here, or our angle. Okay, and one other thing to point out here is that the solution set are in these curly brackets here. All right, they're in the curly brackets. All right, so that's just a notation thing that you'll have to get a little bit more familiar with if you're not already. Okay. And again, basically, arc sine of 1/2 and sine to the negative 1 of 1/2. All right, both are saying, okay, hey, what angle x does this equation satisfy, or where is sine going to be equal to 1/2? All right, where is sine going to be equal to 1/2? At what angles? All right, and hopefully you have your calculator somewhat near you, or at least you can imagine what I'm going to say here. all right, on my calculator, I'm looking at my 84 and my 83 plus, okay? If you find where you have sine, cosine, and tangent, you look where you have sine, cosine, and tangent, okay? Above them, for me, it's in blue because that's what my second color is, but above them, all right, is written the sine to the -1, cosine -1, and tangent -1, okay? So if you needed to plug this into a calculator, you would hit your second button, and then for this example here, we'd hit second sine, right? And it's gonna pop up with this sine to the -1 notation here, okay? However, it's not going to be too terribly helpful here because when I plug in sine -1 equals 1/2, it pops out a value of 0.523598, like really long decimal, okay? It pops out a number that's not super helpful, okay? Except for if I know the values I'm looking for. So if we knew,
Here you can see that theta.
right, if we knew that it was going to be 5 pi over 6, right, we could plug in our calculator 5 pi divided by 6 and see if it matches up to the value, all right? And for the first one, it doesn't.
Are these the only possible angles that?
Okay.
It turns out that pi over 6.
Ooh, sorry. All right, but if I plug in pi over 6, all right, that gets me my value. All right, so when you plug it into your calculator, it only gives you out one value, and it only gives me out this first value that it comes up to. All right, so again, it's good for getting one specific value, but it's not super great for giving you the entire solution set or all possible answers. Okay, so again, you can plug this function in sine -1 of 1/2 into your calculator and it'll pop out one value for you. Okay, so again, you can check it and it's great. Again, you can check a value, but it's not great if you, need to give me the entire solution set. Okay. And again, the reason this is because if we look at our sine or cosine function graphically, again, it repeats multiple times. So there's multiple places, obviously, where y is going to be equal to 1/2 here. All right. So we have to then talk about what does this look like graphically. Okay, what does this look like graphically? I can look at it and yes, I can plug it into my calculator or I can find it on a unit circle, but what does it look like graphically, right? Or how can I determine it using a graph here? All right, so if you were given this graph and you were told to solve for sine of x equals 1/2, all right, what we could do is you could also plug it into your graphing calculator and generate out this graph. Or if this graph is given to you, awesome, we can just use it the way that it comes. So let's take a look at what we would do here. All right. We would be able to look at the intersection points, right? Or if we had this line at y equals 1/2, all right? We can then look for all the intersection points, all right? And yes, if you plug this into your calculator, all right, if you plug in sine of x equals, if you plug in y equals sine of x, all right, if you plug in y equals sine of x as a graph, all right, and then you plug in y equals 1/2, all right, when you get to your graph tab, right, when you get to your graph tab, all right, if you look to the left of the graph button, there is a trace button, all right, there's a trace button. Above trace, it says calculate, it says C-A-L-C in blue, all right, so you can hit second trace or hit the calculate button, right, and what it'll give you the options for is calculating values, zeros, min, max, intersect, dy over dx, or f of or the intersection of f of x of dx, right? You can calculate, you can literally hit calculate and find the intersection points graphically. Okay, so you could find it graphically using your calculator there. All right. And what you'd be able to do is you'd be able to actually find these points graphically in your calculator. All right, and every time you hit enter, it would just go boop, 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 walk you over to every time where they intersect. All right, and so this method is obviously going to be called the intersection method. All right, but you could see that after a while, it's going to keep repeating and repeating and repeating. It's going to be kind of laborious to do this. All right. So what we can do is look at a list of the solutions that we generated just on that first page, okay? And we're gonna try to see if there is a pattern, all right? And when we look at all of them at once, it doesn't look like there is a super great pattern here. But if we click every other value here, all right, every other value, okay? Hopefully you can start to notice something, all right? And I kind of already told it to you on the earlier page here, all right? But the difference between each of these values here is 2 pi, right? It's 2 pi. Because again, our original equation here, our original answer was this pi over 6, all right? It was pi over 6. But we went around once, we got to 13 pi over 6. We went around twice, 25 over 6. Or we went in the reverse direction, right? And so this pattern here starts with our original angle, and it's plus 2n pi, where n is any integer, right? Any amount of times we want to go around our circle. So this would be 1n, or n equals 1. This would be n equals 2. This would be n equals -1, n equals -2, right? So we can find our pattern based on that. All right. If we do the same thing with our other point, clicking on every other point here, all right, the values are evenly spaced out, and guess what? It's going to be the same distance between them. It's going to be that 2 pi distance between them, all right? And hopefully you notice it looks like the same stinking equation here. All right, it's our original angle, 5 pi over 6 plus 2n pi. All right, plus 2n pi. Okay, so hopefully you're noticing a pattern here. They're gonna be the same. All right, so what we can say is, all right, what we can say is that our formula is x equals pi over 6 plus or minus 2n pi, and x is equal to 5 pi over 6 plus or minus 2n pi. All right, and what this is saying here is we have our original two angles of pi over 6 and 5 pi over 6. All right, but we also have every single possible coterminal angle for both of these numbers, right? That's what this plus or minus 2n pi means, is every single coterminal angle is also included, okay? So rather than having to write out a big list, you just find the first values, right? The original values on our unit circle here, all right? And then you write this notation of plus or minus 2n pi for it to represent all of the coterminal angles. Okay, so then here, looking at inverse relations, all right? So like I said here, you can write that as sine to the -1 or arc sine, all right? And what we can do here is to write it in a general form, all right? If we have y equals sine of x, right? Or sine of x equals y, all right? In order to find a solution set for it, all right, we write sine of -1 or arc sine, right, of y equals all of the possible values of x, all right? All of the possible values of x. All right, and this notation here is called our inverse relation, all right, or our inverse function, all right? So this is our inverse function, all right? And in general, remember, an inverse function is where we flip our x and our y values, right? So we flip our x and our y values, and we denote it with that -1 sign, right? This is f of -1 standing for our inverse, which is why, again, this sign of -1 should look kind of familiar. All right, awesome. And sine of -1y does not denote a function, but rather it's a relation, okay? So it is a relation saying, all right, if I solve this, this gives me every value of x that could possibly solve this equation here, all right? That could possibly solve this equation. All right, and obviously it's going to be the same for the other 5 trigonometric functions. All right, so we can have an arc cosine, we can have a arc secant or cosecant, right? Or you can just write them as cosecant to the -1. All right, and again, the cosecant, secant, and cotangent. Okay, obviously we don't have a way of doing that on our calculator directly, so we'd have to use other relationships that we know in order to get that, and we'll work on that a little bit later here. All right, but the -1 notation up here is not saying I take sine to the power of -1. All right, you have to specifically use the sine -1 button, which again can be found by hitting second sine. All right, or cosine -1 is found by hitting second cosine. All right. So again, keeping that in mind there. All right. And you can go through this. I'll just point out one here. All right. But basically what this is saying here is that if I look at arctangent of pi over 3, right? If I look at arctangent of pi over 3, I write my solution set as this value here. All right. Pi over 3 plus n, or sorry, 2n pi, and then 4 pi over 3 plus 2n pi. All right, because again, these 2 original angles are where originally you can find this arctangent of square root of 3, right? And then the plus 2n pi is saying every single time I go around, I'm going to have another angle. All right, so again, looking at if I look at how to solve this, all right, so for tangent, all right, for tangent, I can see that tangent is found there. All right, I can see that tangent is found at both of these points here. All right, so again, every angle that's coterminal to this will give us our solution set. So that's why we write the plus 2n pi there. All right, that's why we write our plus 2n pi. All right, and again, I could have written this, or they could have written this as tan to the -1 instead of arctan. All right, but it means the same thing here. All right, so now that we kind of understand a little bit more about how do we solve those, right, or how do we find the answers to them, now we need to look at how do we actually graph these inverse functions. All right, how do we graph these inverse functions? All right, and we'll take a look at it here, but what's going to have to happen is we're going to have to shrink our domain, right, or restrict the x values that we have here. All right, and the reason that's going to be is because, remember, in order to have an inverse relation, right, it has to be a one-to-one function. All right, and that's bringing back some stuff from semester 1 here. All right, in order to be able to graph the inverse function and to still have it be a function, right, our original needs to be that one-to-one function. So if we look at a quick review here, right, the inverse to the function y equals x cubed, all right, is going to be, we would solve that by flipping our x and our y values and then solving. All right, so we end up with x is equal to y to the 1/3. All right. All right, so if we look
You may
here,
recall that to graph the inverse of a function, you need to reflect the graph across the line y equals x. This is equivalent to reversing the roles of the variables x and y.
okay, remember we talked about reflecting, all right, across again, like you said, this dashed blue line, which is where y is equal to x here.
This will work for all 6 trigonometric functions. In each case, the graph of the inverse relation does not give a function since it does not pass the vertical line test.
Okay, so right now this is a function, all right, because it would pass our vertical line test. But if we flip the function, obviously this does not pass our vertical line test, all right? And all of them are going to do the same thing here, all right? They're not going to pass our vertical line test if we look at all of these guys here, all right? So what we're going to have to do is we're going to have to restrict the area that we can look at, all right, in order to still make this a function, all right? So if we look here again, our black is our original sign of x, and then our red is our arc sign or sine to the -1 of x, okay? Looking at them on the same plane here, all right? And moving forward, we're going to consider x as always to be our independent variable and y to be our dependent variable, all right? But again, what we should notice here is that that red, our inverse, is no longer a function here, all right? So what we need to do then, like I said, is we need to restrict the domain of our trigonometric functions, or we need to limit our x values that we put in for our trigonometric function, okay? So if we look at this here, we're gonna have to restrict it to a one-to-one function, all right? A one-to-one function. So how do we do that here?
Every function has an inverse relation. To graph the inverse relation, you simply reflect the graph across the line y equals x. The red graph is not a function since it does not pass the vertical line test. Flip the red graph back to the original function to see how the vertical line test becomes the horizontal line test for the original function.
Okay, so things we already know. All right, so again, what we can do now is restrict the domain of this function so that it is a one-to-one function. All right, and there's many ways to restrict the domain. All right, however, we generally have a standard accepted restriction, all right? And that one is trying to keep it in quadrant 1, all right? If at all possible, the standard is to try to keep it in this quadrant 1. And the reason that is because obviously we have positive x values and positive y values here, all right? So if we look at our function, right, if we restrict our function, our original function, to just being greater than or equal to 0, right, we now have a one-to-one function that will pass our horizontal line test. So when we invert it, right, or we take our inverse, okay, we now also have a function here. Okay, we now also have a function.
Note how the range of the function f becomes a domain for the inverse relation. When restricting the domain of f to get an inverse function, it is important to restrict in such a way that the full range of f is still achieved. In this case, the inverse function will have the largest possible domain.
Okay, and what that's saying there too is obviously you noticed that that graph went up and up and up and it kept going. So originally, like I said, we're going to try to keep it in this quadrant 1, but we also need to make sure that we represent every single y value. Okay, we represent every single y value. So right now, if we only restricted our graph from 0 to 1 here, or it looks like 1.5, okay, we wouldn't be doing this graph due diligence, all right? Because obviously, a lot more happens as we continue out further, all right? So you have to make sure that you're representing the entire range, okay, or every y value in your original expression when you start to limit the domain here, okay? And what that's going to look like, okay, there are multiple places that we can restrict these functions here. So if I restricted right there, great. Another example, we can go a little bit larger, okay? And I'll let you click through that on your own here, all right? But remember, we've got to make sure that we represent our full range, okay? So some of those were shorter, some of these were even half of this, right? We've got to make sure we represent our full range here, all right? So if we look, when we restrict our domain of sine, okay, like I said, we generally want to try to stick to quadrant 1 here, but as you notice, if we only started in quadrant 1, we're only representing the positive half here and not the negative half. So our answer for restricting the range is going to include this value here from -1 to +1. All right, this value from -1 to +1, because that's our full range here. All right, that's our full range here. And when we flip it, okay, we're still able to get a function there. All right. So again, our range in this original is -1 to +1. All right, and obviously our range in our original becomes our domain in our inverse. All right, it becomes our domain in our inverse. All right, and here our domain is restricted from -π/2 to π/2, and that now becomes our range in our inverse, right? Our x values now become our y values. All right, same thing with the cosine function here. All right, same thing with the cosine function, but luckily for the cosine function, it starts at 1 and goes down to -1. So this is where we restrict our cosine function. All right, again, we still get the full range here, all right, and we're able to then make our inverse as a function. All right, so again, flipping our x and our y values here. All right. Now, there is something I need to point out here. If it starts with a capital letter, right? If it starts with a capital S or C, or in arc sine or arc cosine, it starts with a positive, or I'm sorry, a capital. All right, that is saying that you have restricted the domain, okay? You have restricted the domain, and it's making it a one-to-one function, okay? So when you are talking about sine with a capital S, sine -1 of x, all right, that's talking about a restricted area, okay? So again, the inverse function of sine, as we saw when we restricted it, okay? When we restricted it, it only had this domain here, right? It only had this domain, right? Versus if we just wrote sine of -1, it would have a much, much larger domain, right? Unrestricted, all right? So again, you got to know the differences here where if it's not capital, right, it's the entire inverse relation or inverse function, okay? When you have it as a capital, it means the domain is restricted, all right? The domain is restricted. And obviously the domains are going to differ in their restrictions based on the graphs like we just saw on page 10 there, okay? So then here, if we look at our other trigonometric functions here, okay, we are going to do a very similar thing with these other trigonometric functions. Okay, so if we look at tan of x versus arc tan of x, okay, how could we restrict it to get our one-to-one function? All right, and obviously we would just focus on one of these, all right? The range for tangent is -infinity to +infinity. So when we go to our inverse, we need to make sure that we have a domain that looks from -infinity to +infinity. All right, so again, we just focus on one of these. All right, when we look at cosecant, right, when we look at cosecant, an arc of cosecant, all right, we can clearly see that this range here goes from -1 to -infinity and from 1 to +infinity. So the question is how can we limit this in order to make sure we still cover that range there? All right, and what this is going to look like here is it looks like two disjointed graphs. All right, it looks like two disjointed graphs here. All right, but it still allows us to cover the entire range that we need, -infinity to -1 and 1 to +infinity. All right, without having any overlaps in our vertical line test. All right. If we look at secant and arc secant, it's going to do a similar thing here, right? It's going to do a similar thing. Okay. But obviously this one is starting at 1, so we'll keep moving in that positive forward direction. All right, and then looking at cotangent, okay, you can probably expect it's going to do something very similar to tangent, right? So it'll just cut out and it'll look at one of these specific graphs here, okay, for the restricted domain. All right, so then this is going to be your best friend for this unit here, okay, this little summary chart. It's going to tell you the domain and ranges for the restricted trigonometric functions. And again, you know it's the restricted function because all of these are starting with a capital letter. Okay, they're all starting with a capital letter here. All right, so this is telling you the domain and range for the restricted inverse trigonometric functions. All right, and obviously, as we know, these would get flipped for our regular, right? If we were looking at sine of x originally and we were just looking at the restricted, the domain would become the range and the range would become the domain. All right. Okay. And for example here, all right, it says a thorough understanding of these values of the domain and range are extremely important. For instance, you might think that an inverse function simply undoes whatever the function does, which is true in a sense, but it's not so simple, okay? Because for example here, if I have capital inverse sine, right? And sine of 2 pi. Okay, it cannot equal 2 pi. All right, because 2 pi is not within this domain here. All right, we're between -1 and 1. All right, so we would have to have our value here, instead of it being 2 pi, it's actually 0, right? And yes, those are both denoted at the same place, right? They're both denoted at that same place as being on that first line in our unit circle here, but they're not saying exactly the same thing here, right? Those are those co-terminal angles. All right, so again, knowing these are going to be super important. All right, so then I will let you guys practice these functions. Okay, so practice the relation versus function, because I think this one is going to be super, super important, making sure that you guys can click on these and actually go through this activity, because as much fun as I love, you know, talking these through with you, I think the best way for these guys, since they are a little bit conceptually more difficult, the best way for you to really understand these is to try them out on your own here, okay? So then again, if we're going to evaluate trigonometric functions, sometimes you need to look at them in multiple forms here. So I am looking at, I've got tangent of inverse cosine of 4/5. All right, so what does that actually mean here?
Consider this example. This notation means that you are asked to find the tangent of the angle whose cosine is 4/5. Use your calculator to see what this answer should be.
Okay, so you can legitimately just plug this into your calculator here, all right?
If you do not have access to a calculator, you could go back to the basics of right triangles to calculate this directly.
Okay, so you could calculate it out, all right, and then figure out, okay, you could figure out that this is going to be a 3 here based on your Pythagorean theorem, and then you can solve using tangent now that you've got your right triangle.
Try to extend the reasoning of the previous example to this situation. Here, there is no possible way to calculate the angle given by tangent inverse of x. You have to rely on right triangles.
Okay, so again, not as nice here, but you can still do it, right? You can still do it. And it's saying, again, tangent of, or what angle would give us tangent equal to x, right? And that's going to be obviously x over 1, right? Opposite over adjacent, all right? And then we can use Pythagorean theorem to solve for the hypotenuse there. Again, then we can say sine of this angle is going to be opposite over hypotenuse. All right, so then again, understanding this, you can then solve the other 6 trigonometric functions. All right, so what this is saying here is just tan of x, right? Or what angle gives you tan of x, right? And this is that angle. So for all of those where it says tan of x, it's just talking about this angle here, and it's talking about this triangle, right? And everything is in relation to this angle here. So now that you've figured out this triangle, you can do the other 6 trigonometric functions here, right? Pretty easily, I hope. All right. So then if we went back to this watering the garden example, okay, we now would be able to solve for that angle that we were solving, right? We could use our arc sine or our arc cosine to figure out the angle. And then as we found out, it was double the angle, right? So we could again figure out what tangent is. Tangent of theta would be, 6/2, right? We could then figure out what is tan to the -1, or what is arc tan of that angle. Once we've got that angle, we just then double it, because it was half here and half there, right? So we could figure out that angle there, okay? And again, to review, this is where you're going to go back to that summary page and just be able to match those up, okay? I don't ever expect you to memorize these, okay? Have them on hand. It's going to be super helpful. All right, quickly here then, glossing over the study sheet, all right? Glossing over the study sheet, especially for this one, when there's a lot of values that are very similar, this study sheet is going to be super helpful, okay? The first questions here talk about solving for, our angle on a unit circle, okay? And then finding those coterminal angles, all right? Finding those coterminal angles. All right, and understanding that when we're dealing with finding the angles, we're dealing with arc sine, or this sine to the -1, which is both representing our inverse. All right. We can use our graphing calculator to give us one single answer. We can use our graphing calculator to make a graph, right? And use that intersection point. All right. These are talking about all of those inverse relationships here. All right. And then when we have to make it into a function, when we have to turn it from this relation into a function, right? We have to restrict our domain in order to be able to satisfy the vertical line test here. Okay, we have to be able to shrink it in order to satisfy the vertical line test here. All right, so then moving forward here again, talking about domain and ranges, those are those summary pages. Okay, those are going from that summary page. And again, I would suggest taking a screenshot or adding that in on this side here, right? That's going to be really, really helpful for you. Okay. Perfect. All right. And then we can then find answers to trigonometric functions when it looks like this. So this is saying figure out sine of inverse tan of x over 3, or what is sine for the angle where tangent would give me x over 3. All right. So again, we can draw this triangle here. And if this is my angle here, tangent has to be x over 3, right? So x over 3. All right, I can use my Pythagorean theorem to solve for the rest of my triangle, and then I can figure out my normal functions, my sine, my cosine, my tangent, arctangent, right? Cotangent, all of those trigonometric functions here. All right, and then here again, this was our garden problem, right? This was our garden problem here. Okay. All right, awesome. So this is our study sheet here. And then finally, our checkup. All right, again, I really highly suggest that you do the checkup on this one so you can check yourself, because again, I know that this gets really confusing really quickly. All right, so stating positive or negative sine, cosine, and tangent functions in each quadrant, right? So that's dealing with what's the x value, what's the y value, okay? Positive, negative, negative, positive. All right, looking at solving this equation, right? So figuring out the angles that make this true, but you have to look for the restriction of 0 to 2 pi, right? So that's talking about one complete unit circle, right? One complete unit circle. All right. 8 and 9, it's asking you to actually use your calculator. So you're going to calculate an approximate value. Again, approximate because it's going to give you a decimal with multiple numbers there because you're dealing with units of pi, right? So you're going to just round those out there. All right. When it says find the exact value, okay, that's talking about pi over something. So here, notice, approximate value is talking about decimals, all right? And I'm assuming, okay, this is going to be like 1.51025, like really long decimal. Okay, you're going to approximate that by rounding. When it's talking about exact values, that's going to be talking about units of pi, right? So pi over 2, negative pi over 4, actually giving exact values there, okay? Then again, 15, 16, you're going to do the exact same thing where you figure out what this original angle would look like on your triangle, and then you solve from there. All right, you would solve from there. And then here, hopefully what you can notice is I've got tan of x minus square root of 3 equals 0. Okay, so the first step is you have to isolate your x variable. All right, so notice, you're going to isolate your x variable by making it tan of x is equal to square root of 3. All right, and then you're going to use your inverse function. Okay, you're going to use your inverse function to figure out what are the 1 or 2 angles on our unit circle that give us this expression here. All right, and our 2 angles that will give us tan of x equal to the square root of 3 is this pi over 3 and this 4 pi over 3. All right, then since it says describe all of the solutions, all right, all of the solutions, that's where we have to add on this plus 2n pi. term, all right? Because this is saying every time I go around, it's going to stop at this pi over 3 terminal, all right? And you're going to find it's going to be the same thing with all of these, all right? So isolate your x variable, all right? Isolate your x variable and then solve from there, all right? Isolate your x variable and then solve from there. The last one that I want to point out here is number 20. So I've got sine of x, cosine of x, all right? This is our zero product rule, right? This is saying where sine of x is 0 or cosine of x is equal to 0, all right? So you figure out where both of those are equal to 0, okay? And that's your solution set, all right? Anytime, any interval of pi, right, is sine of x is equal to 0. And for cosine of x, anytime x is equal to pi over 2, right? But for this one, okay, again, plus n pi, all right? Plus this n pi, all right? Again, sine of x is equal to 0 at 0 and at every iteration of pi. So it already has that. It'd be like saying 0 plus n pi or pi n, okay? So again, I really suggest that you take a look at this and try this out here, okay? And we're gonna end class here because again, I feel like that one was super, super meaty. It took us 50 minutes to go over it. So I just wanna end class there so that you guys can focus on that one, all right? You have one quiz for this one, all right? And then tomorrow in class, we'll cover 3.2, 3.3, and I'll release you to do your quizzes for both of those and then the unit test, all right? So tomorrow will be a little bit more involved because today was a pretty hefty unit here, all right? So